So I would like, first of all, to thank the organizer for this very nice workshop and to give me this opportunity. So I'm Pasquale Scarlino. Now I'm working in ETH Zurich in the group of Professor Warraf. But the work that I would like to show you today was part of my work during my PhD, done in the Lieven van der Stappen group at the TU Delft in collaboration with another PhD student, Erika Kawakami. And we also benefit a lot of for the very fruitful collaboration with the group of Professor Mark Erickson at the University of Wisconsin. And on the theory side, for the collaboration of Susan Coppersmith and Mark Friesen, always at Wisconsin University. So this very nice poster allows me to place right away my talk. So unfortunately, I'm not going to tell you anything about acoustic, but what I'm going to focus is this specific solid-state qubit that someone maybe in the future would like to couple with a surface acoustic wave resonator, following the scheme that has been shown yesterday by Martin in his very nice talk. And specifically, what I would like to show you is how to control a single electron placed in a silicon environment. So in this community, one very important work was this very important paper from Daniel Loss and SiGe DQD in 1998, where they show all the ingredients that you need to use in order to control and to encode information in a single electron spin confined in a solid state and semiconductors. It took almost 8 years to reach the first experimental realization of a single electron spin rotation done in Delft by Frank Lopez and co-worker. And as has been already explained during this conference, in order to do electron spin resonance, what you need is a static external magnetic field in order to remove the spin degeneracy, and then an AC oscillating magnetic field perpendicular to the external static one. And if you look at this figure, the way they were creating this oscillating AC field was by using this very bulky wire, which is a strip line, which is built on top of the double dot structure where they confine the electron. And to send just an AC oscillating current through this strip line, they are able to create, just for Ampere lab, this AC oscillating field. But if you want to look for scalability, this kind of solution is not so easy to implement because you need to have many of those strip lines next to each other. So what would be nice is to perform electron spin rotation by using AC oscillating electric field, which are quite easy to produce. And this has been also shown in depth in 2007 by Katia Novak and co-worker. And in order to couple the electric field to the spin, you need a spin orbit-like mechanism, as has been explained in the previous talk. And in gallium arsenide was relatively easy to do because there is the natural spin orbit field due to the Rashba and Dresselhaus. But we would like to use now silicon for other reasons that will be clear soon. And in silicon, due to the crystalline structure, which is cubic, the spin orbit field is almost 100 times smaller than in gallium arsenide, so you cannot use this. But you can still do something because following the proposal of Professor Tokura in 2006, you can create an artificial spin orbit field by using the gradient of magnetic field generated by a micromagnet geometry just placed on top of your structure. And this is actually the solution that we followed. And this has been realized by the first time by the lab professor Tarucha in Tokyo. So during the last 15 years, really a lot of very nice experiments have been performed in this field by controlling the spin of electron confined in a single dot, double dot, triple dot, quadruple dot, and nowadays also 5 and more. And, but all of those experiments were mainly performed in gallium arsenide, aluminum gallium arsenide TUDEG. And by using 3-5 semiconductor material, there is an intrinsic limitation, as has been pointed out already before during the talk of Professor Fujisawa, which is that all of those elements present a nuclear spin. So what happens is that your single electron spin is continuously interacting with a slowly evolving bath of nuclear spin due to the hyperfine interaction. And this is causing the Zeeman splitting to fluctuate. This finally is giving the coherence. And the typical T2 start, so the coherence time for a single electron confined in gallium arsenide are of the order of 10 nanoseconds. But fortunately, the nature offers other materials, such as silicon, which are pretty suited for this purpose, because actually natural silicon is already composed by 95% by silicon-28, which is nuclear spin-free. And what has been recently shown is that you can even do isotopically purification. So very nice work has been done during the last 2 years in the group, Sydney group of Professor Morello and Zurak, where they were able to confine a single electron in an epilayer of silicon, just silicon-28, 99.99%, and they were able to show extremely long coherence time of the order of hundreds of microseconds. In our structure, in our experiment, we were using just a natural silicon quantum well between two silicon germanium layers. So we were affected by the remaining 5% of nuclei, but nevertheless, we can reach a T2 star of the order of 1 microsecond and dynamical decoupling of the order of 500 microseconds. So an improvement of almost 100% compared to the bare single coherence time in gallium arsenide. So let me just briefly guide through the structure, because on fabrication point of view is a bit more complicated than the equivalent structure on gallium arsenide, because our starting point is an undoped silicon germanium heterostructure grown by Lagali group in Wisconsin University. Why undoped? Because the community understood after the work from HR group that actually using an undoped structure, you gain a lot in terms of stability. So we start with this undoped structure. We deposit an oxide layer, 10 nanometer aluminum oxide. Then on top of that, we make what we call a defined gate structure, which is the one that you can see schematically represented in this picture, where we're going to apply later negative potential in order to shape the confinement potential for our double dot structure and for our charge sensor. This is a dot-3-dot sensor, and this is a quantum dot charge sensor. Then on top of this, we make a second layer of aluminum oxide, 50-80 nanometer, and then again a second layer of metal gate that we call accumulation gate, because actually we will apply to those gates positive potential in order to accumulate the gate in the quantum well below. And on top of everything, we have our micromagnet structure, which we use in order to perform electron speed resonance, as I'm going to show you soon. So this is a schematic view of the side of the device. So there is the silicon quantum well, roughly 10, 12 nanometer, 40 nanometer below the surface. Usually the percentage that people use nowadays is of the order of germanium, is of the order of 30%. And then there is the fine gate, oxide, again oxide, accumulation gate, and cobalt micromagnet. And the ohmic contact are realized by phosphor ion implantation. So this is how a device at the end of the 11-step fabrication process looks like. So there is all of those gates. Each gate, of course, is there for a specific function. If you zoom in and look at the SCM, this is the fine gate structure before placing the accumulation gate on top. You can distinguish still the gate below. And on top of everything, there is the micromagnet. So let's start. What we do actually, even if it was meant to be a structure to create a double dot, we create just a single dot on the right side. So we go down to the last electron. We place just one single electron. Then we apply an external magnetic field in plane in order to split the spin degeneracy, and only to completely magnetize the micromagnet. And what now we can do is to apply an AC oscillating electric field to one of those gates, for example, gate 8 in the figure. And what is happening is that our electron wave function is moving, shaking, inside the gradient generated by the micromagnet. And effectively, in the reference frame of the electron is feeling an oscillating AC magnetic field at the same frequency of the applied electric field. And we read out the spin in single shot using spin-to-charge conversion by making use of this charge detector. So what happens is that the current flowing through the charge detector can feel the presence or the absence of the electron in this quantum dot. So if the electron jump out, the current in the charge detector increase. If the electron come back, the current come back. So you can see those steps in your charge detector, and then you can realize, okay, there is an electron jumping in and out of my dot. So we can initialize, manipulate, and read out our single electron spin electrically by using the following pulse scheme. So what you can do, you can apply a pulse to one of your gate to move the relative position of your Zeeman level with respect to the Fermi reservoir where the electron can jump in. So what you do in this step, the empty step, you bring both of those levels higher in energy with respect to the Fermi level. So doesn't matter what spin was inside, the electron will jump out. Then you go in initialization. So now just the spin ground state is below the Fermi level, so you mainly feel spin ground state. Then you go deep inside Coulomb blockade, where you're going to apply the high-power microwave burst. And you do this in order to avoid to kick out the electron due to photon assistant tunneling. Then you come in the readout, where you ask your electron, what is your final spin? And if the answer is, I'm in the ground state, the electron stays inside the dot. So there is no change in the current through your charge detector. If the answer is, I'm in the excited state, the electron is going to jump out, and so you see the changing the step in your charge detector. So what you do is actually you repeat this pulse scheme over and over, 100, 1,000 times, and you collect statistics on the number of events during the readout stage, which is going to give you directly the spin excited state probability. So if you scan the microwave frequency, and then at one point you hit your Rabl frequency, you see a net increment in the number of counting. And to show that it's a spin resonance, what you do, of course, is you change your standard magnetic field, and you follow the frequency evolution of this resonance. And you can fit this frequency evolution, but you have to take into account, and now you're using a micromagnet, so there is an offset in your magnetic field generated by the micromagnet. You can extract your electron G factor, which in silicon is of the order of roughly 2. Now you can crank up the power, and you can change the microwave burst time that you apply. And if you have high enough coherence, you can do coherence oscillation. And if in your system, if the Rabl frequency of your system is higher than 1 over T2 star, you can also rotate your system if you are detuned, so you can get this nice chevron pattern. If you make a cut at the Rabl frequency, you see the nice Rabl oscillation, and the decay of those oscillations is due to the remaining 5% of nuclei in the natural silicon. And the maximum Rabl frequency we can get is of the order of 5 megahertz. Of course, you can improve this if you increase the magnitude of the gradient locally. Just for comparison, remember that on gallium arsenide, the oscillations were already dying on the order of 100 of nanoseconds. So now at this point, one can apply all of the technique, borrowing those from NMR community, to try to extend the time, the coherence time of this system, of the spin system. So we did the echo and dynamical decoupling pulse scheme. This has been done by Erika Kawakami. And so what you can do is to increase the number of pi pulses in between, and you can preserve the coherence time longer and longer and longer. If you fit those decay curves using this relation, you can plot the coherence time as a function of the number of pi pulses in the sequence. And what we see is that we get a T2 echo of the order of 80 microseconds and T2 dynamical decoupling for 28 pulses of the order of 400 microseconds. But what is good is that we don't see till this point any sign of saturation. So if we keep on applying more and more pulses, we can extend more. So what Erika also show is, okay, if you want to use your spin system as for quantum computation, one benchmark is actually how good is your rotation fidelity or gate fidelity. So you can estimate those using randomized benchmarking protocols. And I don't want to go into detail, but what we extract at the end is that an average gate fidelity on 99%, which is close to the threshold that you need to apply for a surface cause scheme. But this is just part of the story, because we are working in silicon, and in silicon we need to take into account another degree of freedom, which is called a value degree of freedom. So if we just zoom out a bit, we see that next to the main chevron pattern, there is another oscillation pattern. So the question is, what is this? And then what we can do is to reduce the power and to do a measurement again in CW, to reduce the power in order to avoid power broadening. And so we can clearly solve those two peaks. And the separation between those two peaks in frequency is not constant, but it's changing linearly as a function of external magnetic field. So this is suggesting you that actually those two resonances are two spin resonances that have slightly different G factor. So our hypothesis is that those two resonances are related to the value degree of freedom. So what is the value degree of freedom? So we know that silicon is an indirect band semiconductor. So the minimum of the conduction band is not in the center of the Brownian zone, but it is in one point of the Brownian zone which has 6-fold symmetry. So so the ground state in bulk silicon is a six-fold degeneracy. But once we build silicon on top of silicon germanium, we break the planar symmetry due to the strain, and then we separate two-fold and four-fold degeneracy. But the ground state, in this case, is still two-fold degenerate. If you want to lift this degeneracy, you can do by building a perfect, ideal silicon quantum well. And in theory, this should give you 100 till 1 milli-electron volt valley splitting, which is good enough to operate just with the spin. But what happened in reality is that you have many kind of disorder at the quantum well silicon germanium interface. And one of the most important one are those atomic steps at the interface. And if your electron wave function extends over many of those steps, you wash out completely your valley splitting. You can be even 0. And furthermore, this kind of step disorder introduces what is called valley orbit coupling. So now the valley degree of freedom gets coupled with the orbital degree of freedom. And what does it mean? It means that the orbital wave function for the two valley state gets a bit different. So now we are able to address both of those peaks. So we have valley ground state, both spin resonance, valley excited state, spin resonance. And what is happening in our system is that our valley splitting is almost comparable to our electron temperature. So why we see both of those resonance? Because during the initialization stage, we feel the spin ground state, but we can feel it in both of the valley state. OK, but now what was a very simple system, a single electron confined in a single quantum dot, now got a bit more complicated. There are not just 2 states. Now there are 4 states that are playing this game. And actually, this is reflected in our spin resonance spectrum, which get more complicated. So those are the 2 states that I just explained you. But actually, we have other 2 resonances in this plot on top of each other, but we can clearly resolve them at exactly half of the frequency of the main resonance. And this is already suggesting you that those are nothing more than 2-photon version of the fundamental resonance. So we can drive this energy transition applying half of the frequency required. And this has been already shown in a double dot spin system. But what we showed, we were able to do more is that we were able to use those transitions to drive coherent oscillation. And you can extract the Rabl frequency driving at the second harmonic. And what is nice is that in this system, we get the maximum Rabl frequency driving at the second harmonic, which is just half of the maximum Rabl frequency that we get driving at the fundamental harmonic. So this means that in our system, there is a huge nonlinearity that allows us to do this. And in between those 2 sets of resonance, fundamental and second harmonic, there is another resonance which has a quite peculiar behavior. So what is this resonance? We can identify this resonance as a resonance where we change at the same time the valley degree of freedom and the spin degree of freedom. So this is possible because, as I told you, so in our system we have a valley orbit coupling due to this step disorder, and there is this artificial spin orbit due to the micromagnet, and this allows us to get a second-order valley spin coupling that allows us to drive this transition. And we can use this transition, so the difference in energy between the fundamental spin resonance and this transition can give us directly a measurement of an estimate of our valley splitting, which in our case, we extract is of the order of 300 millikelvin, comparable to our electron temperature. So this resonance, where we drive at the same time spin and valley, is quite peculiar because the line width of this resonance actually is almost 10 times of the line width that we extract from normal spin resonance. So the noise affecting this resonance, those resonances, they are slightly different. We know that the fundamental spin resonance is limited by just 5% remaining nuclei. But the noise affecting this other resonance is also coming from has also electrical nature. And how can we prove this? For example, what we can do is to change on purpose the voltage applied to one of those gates, and we look at the frequency change of the main spin resonance and this resonance where we change at the same time spin and valley. So if we look at the fundamental spin resonance, this is changing, slightly changing in frequency by moving the dot a bit around, because actually what we are doing, we are moving our dot in a different gradient of magnetic field. So the gradient of magnetic field is not constant. But if you look actually the response, the changing frequency of this other resonance, this is much more pronounced. And we can explain this by looking at this model, as I showed you before. So we believe that our dot is quite close to one of those atomic steps. What has been simulated by Mark Friesen in Wisconsin is that, so starting, for example, with your dot far away from this step, you can approach this atomic step interface. And if you calculate your valley splitting, this is going to get a minimum when your confinement potential is right on this step. And then it's going to grow again when you go away from the step. So actually, this resonance, we know that is given by the fundamental spin resonance minus the valley splitting. And this is the reason why it's much more affected by electrical noise. So I hope that I convinced you that if you look, using a single electron spin confined in silicon environment can constitute a very nice qubit. You can get coherence time quite long compared to gallium arsenide. But if you want to use silicon, you need to pay attention, because this extra degree of freedom, the value degree of freedom, can make all of your energy scheme that you have to use to drive transition quite more complicated. So ideally, what you want is to increase your valley splitting several Zeeman splitting to be sure that you are just operating with your single electron spin. And with this, I would like to thank you for your attention.
In one of the original proposals in silicon germanium structures, there was a discussion about defabrication, applying a gate voltage perpendicular to the structure and kind of displacing the wave function into the silicon germanium region.
So actually, this is what, as far as I know, okay. There are groups, also Wisconsin, that are working about on placing a phosphor atom inside silicon germanium too, but for other reason. I think that in that direction, of course, you can do this using a silicon epi layer, as has been done by Morello. But in silicon germanium, I don't, as far as I know, there is not so much work going in that direction.
Just a comment. It's all very nice, but the gallium arsenide is better than you made it look here, because your movie measured 200 microseconds, the 2 time, not 0.5 microseconds.
Okay, this was for single electron. That is single triplet, but I have also an answer. No, okay. But if I'm not wrong, that dynamical decoupling sequence is not for 2 axes. It's just applying pi rotation along 1 axis. And this can lead to something strange. So what you need to show is you can do dynamical decoupling along the both axes to preserve both of the spin component. This is why we do XY, XY, XY.
So actually it has been extended to 1 millisecond, right? In the group of Charlie Marcus recently.
Is it?
Yeah, but this is... No, but okay, but this is not our limit, no? So you can extend even more here. We did not saturate. I mean, what you can do on gallium arsenide, you can do on silicon better. This is the statement.
That's probably true.
Yeah.
Yes. So your valves are split by the strain, and this depends on the composition of the silicon germanium layers. How much you can actually exploit this strain effects to
the first split of value from 6-fold degeneracy to 4 and 2 is due to strain in plane. Then to split the further 2-fold degeneracy, you need to lift the symmetry along the z direction. So, and this is you do by breaking the symmetry, so building a quantum well, or introducing an electric field. Yeah.
Do you know the density of atomic steps in your fabrication?
It really depends from your heterostructure. So no, I don't have a number, but can be in this case can be few atomic step, also 3, 4 in our quantum dot. it depends really from the quality of the heterostructure.
Any further questions? If not, let's thank the speaker.